Hey, what's going on, guys? Kamegi here. Welcome to the new episode of live coding a 6502 simulator in x86 assembly language. So last video we've ended up with providing the tests for LDY instruction. So all the addressing modes are available here. Let me just quickly run the tests from the previous part. So yeah, all done, everything is fine. And now the very first thing to do, I will just move the test. I will dump the test to this unit-test.asm, which is just the file where I dump everything. And then we'll go implementing the STA instruction. So here we have the LDY. Well, it's not, this file is not intended to it's not linked to the app on its own. It's just kind of dumps the code. So if I need to grab the code, I can just take that. That's pretty much all about it. All right, so I'll probably reorganize this later on, but for now this is just fine. Okay, so where are the tests? Here are the tests. Okay, and the STA is going to be bigger than LDX and LDY because of involving also the indirect addressing modes. So save. Okay, now we got LDY, which is great. All right. So yeah, let's have a look. Control F, STA. So here is the STA. So starting from the 0 pages, and then it seems like all the addressing modes that are available for the LDA. So I would probably be reusing the code for LDA, just altering this to setting the instead of loading value to register, would be setting the value to the memory that would be get from that would be gotten from the specific address, right? Okay, so it doesn't affect any flags, so I need to make sure that I remove the code that is responsible to resetting the negative and the 0 flag from LDA, and also of setting 0 and negative flag and resetting them as well. Okay, so I think that yeah, starting from the test 1 for LDA is actually loading the it's loading the immediate data. We don't need this, so we'll start from the test 2. Okay, we'll start from the test 2 where it loads the value from the 0 pages. I'm just wondering, was it actually loading? Was it loading the data from 0, 0 really? So what do we have in LDX? I'm just wondering. Sorry guys, I already completely forgot about it. Yeah, and here, no, this is the, okay. Oh yeah, here I've changed this later on to 0, 4. Yeah, probably. Yeah, we can change. We can create a custom address here. All right, so grabbing this one, and we're gonna be proceeding exactly the same way as in the previous parts. So I just would be commenting out everything, and then uncommenting line by line, altering the output. So here we have the test 001. Okay, so here we want to say STA, and let's set the value to the 0 page address 2, for instance. And now we need to grab the opcode So yeah, we're done with the load operations, these guys, and this is really cool. So now we are in the set operations territory. So starting from STA 0 page, so the opcode is 85, just to remember that, 85. So here we say 85, and from 0 to. So the reason why the byte order is different is that's because of the little endian byte order. So we first have the value to here it is. So this is the big endian representation. Here we have the value first of the 0 page of word to read the data from, and then the opcode. But when it gets loaded into the program, into the simulated memory, simulated 6x2 memory, it would be printed 85 and then 0 to you. We'll see this just right in a moment. So let's have a look. So here we should see the program, this machine code. Okay, so it's not the instant value addressing. So here is a little bit of an issue. And by the way, hold on a sec. So this means that in the previous tests, I was probably, so test instant. Yeah, this was really wrong. Yeah, I just had the wrong labels in the LDA tests along the way. Test instant, 0 page. Oh no, it's not instant. It's instruction actually. Oh no, hold on a sec. This all is. Oh, guys, I'm sorry. No, it's all okay. I just grabbed. I have grabbed the wrong test. I should have grabbed this one. Yeah, actually should have. Yeah, because the one I've grabbed was actually loading the value of 0, not from the 0 page. I'm sorry. So yeah, I've grabbed the wrong test. I should grab this one. So here it actually does load from the 0 page. Okay. So 85. Okay, 85 is the opcode. So paste in. This is gonna be test 1. And 85, and this is gonna be STA to 0 page 4. Yeah, it's okay. Now it's nice, just fine. All right, so let's have a look. Well, I don't want up to execute. This should be fairly enough. Okay, so what we got, so instant 0 page instruction, so the instruction is STA in our case, so 0 page addressing. Okay, we got this 85, which is the opcode for STA to the 0 page of 4, 0, 1, 2, 3, 4, at the 0 page of 4. Okay, so this is a little bit of an issue, so we already have the value being set there. It shouldn't be like this, so let's quickly fix this out. Well, probably, yeah, yeah, I was trying to make it faster, but better not. So actually, let's have a look at yeah, this is the machine code, right? Now I don't want to, so these lines were writing the value of 45 to the 0 page 4 because we were reading that in the LDA instruction. We don't want this now at all. So let's see. So there should be an empty memory. So just to see how this memory looks. Okay, so memory dump. So we get nothing there. Yeah, and the formatting for the instruction is going to be a little bit different. All right. So what else? Now? Yeah, we'll probably need to hard code some value to the A register as well. So let's have a look. What are the initial values for the registers? So yeah, they are they rely on the default values, all of them, right? So program counter starts at 600. Okay. Flags, only the reserved flag is set. All right, so it's okay. So as far as we're gonna be setting the value stored at the A register, so let's actually load some specific value to the A register. So I can simply say move byte to the register A, and let's actually take that 45. So set register A to 0x45 hexadecimal. All right, so yeah, now we have the value of 45 in the A register. So we're gonna store this value here. So after the execution happens, this line, we don't actually need to. No, we still need to print. We still need to print the value after, but also we want to print this exact memory range. So again, like probably yes, starting from here, another new line. Okay, or maybe if this gives us a new line, don't remember if. Yeah, probably this. Yeah, the register is given a new line as well. Maybe not. Okay, doesn't matter. So let's go and implement this instruction first, and then we'll try to, or even nope. So memory monitor is also on the cards. Print memory range. So just want to see the layout, how the layout. Okay, we don't have a new line, but we want to have one. So yeah, let's bring the new line in as well. Okay, so here I would be verifying whether the instruction has worked properly or not. So flags should be the same, only the program counter should get increased by 2 because we have 2 bytes to process, and the value of 45 should get to 0, 1, 2, 3, 4 here. Okay, now let's implement the 85. Yeah, I was just setting the letters to the lowercase for the instructions I've already considered. So maybe maybe I just should use something like implemented. Okay, just for my own self, I just want to make sure that I know which instructions are implemented, which not. Okay, I'm sorry, it's a little bit boring to watch this part, so feel free to skip forwards a little bit. So this is going to be implemented next. Okay, and now I go to execute. Okay. Yeah, so these were, yeah, LDY, and the next. Let's bring the separator in as well. So I want to compare AL, which holds the next opcode to execute with this value. So instruction STA is STA to 0 page, set value to 0 page. So STA 0 page address and opcode jump equals to STA 0 page we didn't yet create this. We'll do this just run in a moment. Okay, so if so, then execute it. All right. If so, then execute it. So STA 0 page. So I'm now looking for LDA 0 page. And here we have LDX 0 page and LDY 0 page. So I need to take a decision, where am I gonna be putting this. So probably right next to LDY 0 page. But on the other hand, probably better like load A, set A, load X, set X. So probably that would be a bit more intuitive way of doing things. So for that reason, I'll drop this just right below the LDA 0 page. So here, so we're gonna be having the STA 0 page address in mode. STA. Okay, so everything is the same apart. So we're getting the value. So yeah, here we're getting the value of the 0 page. We don't need to get the value from the 0 page. We don't need to clear the flags neither. So updating the program counter. This works the same. Yeah, now things are getting a little bit tricky. So what actually, I'm just wondering what this call get 0 page do. Let me recall. Call it should be returning yeah, it returns the value at AL. So probably, yeah, get 0 page value. Okay. I'm just wondering if I can reuse this without creating the set 0 page the value to 0 page. So here it gets the 0 page addressed. Okay. Okay, yeah, here it loads. Yeah, unfortunately, I will need to re-implement this. Yeah, so this is gonna be tougher as opposed to the previous part, so I'm forced to write some code. Okay, it's okay. So yeah, actually I would need to rewrite every single one. Yeah, here AL only holds the value that was read there. But on the other hand, hold on a second, guys. I'm just really wondering. Yeah, it did increase the pointer. Well, I mean, like, I can potentially reuse it, but get 0 page. Oh no, I can't, because SI has been popped already. Yeah, it's better to write a new one. Okay, so in this case, what we're gonna have, yeah, it's logical to write that. Okay, so we don't want to set any flags because 0 page addressing. Yeah, we don't want to set any flags because STA does not affect any flags. All right. And here, so we're not going to load the data to the register either. So these lines are needed to set the 0 flags. So, or negative flag, we don't need that. So jump, execute debug, and yeah, and this is right. But hold on a sec, guys. I just thought if maybe I can embed the code just here. I don't probably even need to Yeah, all these design decisions are a bit tricky to consider, so yeah, I'm sorry for not knowing how to do this instantly, because I've never been doing this before. So this is the live coding, so I have no idea what am I gonna come up with eventually. Okay, so I mean, the reason why I have separated this to a single function was because so we'll have this in STA, but we'll also have this in STX and absolute as well. So absolute would be reused 3 times. 0 page, so absolute addressing is reused 3 times. The 0 page is reused 3 times, and 0 page X is reused 2 times, here and here, in LDA, in STA and STY. Okay, so yeah, I was also separating the getting direct. Well, probably let's follow this tradition, actually. So addressing modes, 0 page. So this is actually should be treated as, oh, sorry, what have I done? As get addressing modes, right? And now we need to make the same, but with the set addressing modes. Yeah, probably so here we have the set addressing modes. Yeah, just the right place. So we don't need this. What? Oh no, it's okay. Here, starts from here. So get the 0 page, and we don't have the get immediate because this was the part of LDA immediate, I believe. Yeah, because we just got it from there. Okay, all right. So we'll use this code to get the 0 page value, and we will alter it to set 0 page value. Copy and paste. So here we want to set the 0 page value. Okay, now let's recall the code that I've been writing a couple of days ago. So clearing adding AX to memory. Yeah, so all this stuff. So get the 0 page address simulated in the simulated memory. Okay, preserving DS. Okay, XOR. So everything before so to SI. Why was I loading point SI to 0 page address? Okay, so AX now points to the 0 page address. So here here I'm not sure about. I need to store a single byte, and that byte should be stored in AL, and in AL we need to have the value from the A register. So that's what I want to say. I'm just wondering what's the better way of doing this. Let me think a little bit. Well, I can actually print the word, so push all, pop all, and call procedures print word, and by doing this I will know what I have in the AX register, so whether AH is free or not. So to figure out if I still need to reset that. I've been resetting I've been resetting AH and edit AX to memory. It should be, but yeah, let's just make sure it is really so. And where is my STA? Where is my STA 0 page? Here it is. So here I want to go to call set 0 page value, and whatever we have in a register, well, it won't get set immediately but instantly, but at least it would hopefully bring me some debugging information. And I want to call execute now. Let's have a look. So here is what we have in the AX. Okay, we have the global address, we have the address. So yeah, we just in this case, Control F, set 0 page value. So in this case, we want to XOR AX. We want to move byte to move to AL. I want to move the byte from the register A. Okay. And then I will call store single byte after. And let's print. Yeah, we can still print the word. It should be 0, 0. Why 0, 0? Oh, that's because the scope. Okay, hold on a sec. So before we push the DS, let's preserve this. Say to where have I been preserving? Yeah, for instance, yeah, this is what I need. Yeah, so I can say, yeah, let's say XOR, let's store it to BX. So BX, move to BL, the byte, the register A. Okay, so now BL contains the value of register A. So here I want to reset BX and store the value of register A in BL, the lower 8 bits of the BX register. Okay, and here XOR in AX, and instead of this, we just to AL we want to move the value from BL, which is the problem is that we just switch the data segment from 0 to the scope of the current file to reference either the local variables or the variables within the entire segment. And here this happens before we actually this happens before we push in the DS and altering the DS, so the DS gets reset there. Okay, so AL, yeah, and now print word should print 0, 0, and then the value of the register. Okay, register, not the register, but the register. It should now print 0, 0 in the register. Yeah, 0, 0, 45, which is correct. And just to make sure, we just print the byte instead. So it's like how useful this debugging functions occur to be. Yeah, 45. And now we can safely, so as far as we have this in AL, we can just store single byte. So we want to set byte and 0 page address, set the value of a register to the 0 page address. Set the value of a register to 0 page address. Okay, this should be fairly enough. And also, so we don't need this debugging stuff anymore. And here, so we just reset AX. Move, let's say set AL to the value of a register, because BL holds that value since this line. Okay, now this actually should already do the trick, but it doesn't for some reason. Okay, after execution, this is very strange, to say at least. Oh, guys, that's because, okay, hold on a sec. Yeah, that's because I've just or hold on a sec. The SI actually should be. Well, I cannot use in the store single byte. Well, this is so. Oh, it's oh my god, it's not SI, it's DI. It should be DI. It should be DI. But do I really need that? Do I really need those complications? I'm not actually forced to. Yeah, the idea is that here is the deal. So the idea is that by I was using this load single byte, and this was moving the instruction pointer to the next. Or was it? No, I actually didn't. Yeah, as far as I did push and pop. Yeah, this doesn't actually affect anything. Okay, this is already a much better thing. So okay, if so, well, I don't know. I could have involved DI to just use this single byte store single byte, but on the other hand, I can do this manually. And as far as I don't care about the SI, I can even probably not be pushing the SI. Okay, guys, I'm sorry for being a bit dumb here. So again, I just want to print Word procedures. All right, so what do we have here? So this is the, okay, so currently AX holds, at this point, yeah, AX holds the value of the address, so as the SI. So if I say move single byte at DSSI from BL, which stores the value of the A register. Is this gonna do the trick for me. I think it should. It should make the trick. And it does. So here is the value. And I probably don't even need to push and pop SI here. Well, without actually executing the next instruction. It's hard to say. So if I'm running an instruction at a time, this shouldn't matter really that much. But the problem is that SI initially, SI is pointing to the next instruction, I believe. So okay. So what I've been doing so far. So this load single byte was affecting the SI, but I was popping this back, restoring the value of SI. Okay, restore current 652 program byte pointer, the pointer to the next program byte program opcode pointer. It's better to say program opcode pointer. So yeah, it was pointing to, and as far as I don't really change that. Yeah, let's try to comment this out, and I can actually print that. I can print that. So again, so I won't say move to AX. So we don't care about AX anymore, right? And actually, hold on a sec. If this probably I don't need that all of that code. No, I needed to reset the DS to 0. Yeah, in order to make this work. Yeah. And but hold on a sec. I was popping AX already. So I could not push the AX because I don't really need that. I don't need to pop that. So I can just reset the AX. So this is going to be still the same. Nope. This is a bit strange. Oh, yeah, because of this line. Yeah, so actually we needed to do this. Yeah, because AX was holding the memory. Yeah, okay, all right, so, sorry. Yeah, so actually, yeah, we are forced to push and pop AX because it holds the 0-page memory address, which used by SI later on. And then we set the value, okay. Which means okay, which means that SI is okay. Yeah, we need this push and pop. We need this push and pop. So yeah, we need this because I'll now try to explain why. So print word. So this should still be containing the address E004, which is the address, absolute address of the 0-page. Okay, and if we do this, Control X, if we do this here, that this is going to be a different address. Yeah, and here it points to where the program counter is. Okay, so yeah, actually pushing and popping SI is still absolutely essential, right? So we keep this. I just didn't want to have some unneeded code, really. Okay, and here we want to store the value of a register to 0-page Okay, so far so good. And we don't need this. So let's have a look. Okay. Before execution, after execution, well, probably. Okay, so this only has affected the program counter, which is correct. So flags remain the same, the value is the same. And the only thing that has changed is we have the value of 45, 0, 1, 2, 3, 4 at the 0 page 4. And the program counter after should still be at this address. So I just want to make one last little test, guys. One last little test. I want to print it. Yeah, before providing these test cases, actually what I want to do is I've been changing SI here, so yeah, this test cases actually do affect the SI. Okay, so at very list, in the execute, this might be on the cards. So execute. So here, so it jumps to execute debug, and then it jumps to execute next. So after, so here, if I say move to AX, the whatever is in SI, and this should be printing E602, which is the current where the current program counter is pointing to. So push all, pop all, and call procedures print word. So E602 should be there. Actually E603. Oh, well, this is expected. This is expected because or is it? Okay, hold on a sec. Okay guys, it seems like I've just figured out why this is happening. That's because actually if the STA 0 page fires, we don't get here, and we get here only when it goes through the next instruction, which is 0, so it's intended to terminate the execution. So I think if we put this, I think even this should be on the card, so it should now print E602, and the next run is E603. Is this the case? E6, oh, E601 every time. So did I affect? Oh, I was probably. Okay, it doesn't really matter that much. So if I maybe just before like this, just to make sure I'm not smashing the register values. Some gibberish. Okay, actually, just to give you an idea why the heck am I doing this, all I want to check here, so it's okay, it shouldn't be like, definitely not the right place to check for this debug. So I just want to make sure that several instructions of the same kind would get executed properly, and it just won't drop on the very first one. Because of smashing the SI. So let's say STA 0 page. So let's say call in this STA 0 page. So before, so let's say move AX to SI. So I just want to see what the SI is. So push all, pop all, and word. Yeah, now this is what I wanted to have a look at. So E602 here, which is correct. Okay, so now just to make 100% sure that all this is working as expected, I want to set the value of 45 to, say, the next one, to the next, or to the previous memory cell in the 0 page, to 0 page 5 or 3, 0, 1, 2, 3, 4, 5. Let's say store it to 5, so it would be 45, 45. I'm not going to be including this into the eventual tests. However, I could have actually do that, but anyway, so here, copy test program plus 2 bytes. So STA to 05 and to 05. So if I did everything properly, it now should put the value of 45 here, and it does, and this is so cool. Okay, so we have now 2 instructions. So set the value of A register to the 0 page 4, which it does, and set the value of A register to 0 page 5, which it does as well. And as far as it does, it is capable of processing this instruction. This means that everything is okay, everything is fine with the SI register, so it's still pointing to where the machine code is located, and it's not getting smashed. So I was afraid that after executing the first instruction, it just won't be able to move further on. So that would be an unfortunate scenario. Okay, so print to both. Yeah, this is great. Well, I could have leave this, or I could have, I don't know, just to 4 to 5. Well, maybe let's just keep this as is. I think we can just keep it, right? Okay, now it's a test time. Test time. So regarding the test, so we're not, we don't really want to check the registers here, because we didn't do anything to registers. So the only thing we did, we want to check here is the program counter. So, well, I just don't need to check for flags because we didn't really change those flags. Well, they still might be on the cards, but yeah, so only the program counter makes sense here. It would now fail because it actually should be okay, 04. Yeah, because we have executed, we've passed through 4 bytes, yeah, which is correct. So 04. Okay, let's bring this all done. Okay, let's bring this okay string. Okay, and now I need to test whether this memory locations we actually have the value of 45. And to do that, so I think, yeah, we don't need to check the register. We don't need to so where SI is pointing to, it points to the memory now, to print the memory range, right? yeah, writing this test case is a little bit tricky. So yeah, I need to push the DS. Again, like I need to XOR AX, move DS to DS, move the AX, and now compare byte at DS SI, and I want to move to SI the value of what is there. Well, actually, we already have this memory, but yeah, let's better. Well, I can actually pre-code this, so this is going to be E. Sorry guys, just totally forgot that. I need to have a look at the output again. So E 0, 0, 0, 1, 2, 3, 4, 5, E0, 0, 4, and E0, 0, 5. E0, 0, 4. Compare the byte at DSSI with the value of 45 and jump not equals to. So yeah, I need to create a new error test as well. So how we call it? Test error let's call it memory. Test error memory, let's call it like this. So test error memory. Test, I want to put test failed. Let's call it test failed memory. We don't have that label yet, but it doesn't matter really. So point SI to test failed memory. Procedures print string, print test failed memory message, right, and stuck forever. Okay, stop here. Test failed memory, copy. Test failed memory. Memory failed. Okay. All right. Okay. So let's go to tests back 001. Okay, so jump not equal. So let's try and run this again. So far so good. But let's say we try to compare with somewhat a different value, and this is strange. Should print, well, it doesn't, it actually stuck there. It's stuck. It doesn't print that everything is okay, but it doesn't seem to be printing the error message neither. Yeah, it just stuck there. So why? Test error memory, find next. Oh, whoa, that's because I can't hook up the local variables. So I need to pop the DS first. So here, pop DS, right? Memory failed. Okay, but just maybe not with the capital letters. Just memory failed like this. Yeah, memory failed. And exclamation mark. Yeah, now it's much better. So, well, it's not the case now, but I was just debugging the error message. Okay. So where is my test error? Yeah, so here I just want to, yeah, obviously I need to hook up local variables, because just to make sure that I can reference the local variables, I need to pop the DS, because it was equal to 0 before, to use SI for global addressing within a given segment, right? Okay, hook up local variables. So far so good. So now this should be like this. Okay, and now let's test another one. So here, well, it's not essential really. I can do this, but 0.5, and let's just use some false value. Yeah, memory failed. Okay, and with the true value, then it should pass as well, and it does. Yeah, okay guys, so it seems like we've just successfully implemented this STA for the zero-page addressing mode. Yeah, I'm sorry for it takes a bit longer, I would say much longer as opposed to the previous couple of videos, but yeah, I'm really forced to actually write some new code here. Not a lot of code, but still. Okay, so preserve DS, reset AX, reset DX, point SI to 0 page 4. Okay. Check the value at 0 page 4. If it doesn't match, then how did I failure case stop tests? Yeah, failure case stop tests. All right, and here I've been checking for another one. Okay, I just get rid of this one apparently, and as well as this one. So as far as we are able to process more than one instruction, this is okay. And here we hook up local variables back. Okay. You must be kidding, program counter failed. Oh, no, this is interesting. Oh no, it's okay. It should be now 2, not 4. Yeah, it now should be 2, not 4, because I've just dropped 2 more bytes of the source machine codes. Yeah. Program counter is equal to only 2 bytes has been fetched. These bytes, and we do the print, put the value. Okay, so far so good. Okay, and jump to the test 002, and yeah, this is already going to be the topic of. I will stop this video here. So let me just comment this out apparently. Okay guys, yeah, I would probably just stop here, and we'll be covering the next test cases in the following videos, because it already probably lasts kind of too long. But yeah, just probably a bit of a trailer for the next part. So we're gonna make 0 page and the X offset. Well, so yeah, this is gonna be trivial. So I would be reusing the one that the 0 page implementation I came up with already, and then just be altering this. So this should be relatively trivial to make, right? Then for absolute, yeah, just should be rewrite the code a little bit as well, but literally the same as for the like the 0 page, but just reading the word instead of the byte, or I mean, like, yeah, reading the word instead of the byte in order to get the address. So yeah, the code is pretty reusable so far. Absolute X and Y are trivial, and yeah, there would be a bit of a pain with this indirect, indexed, indirect, and indirect indexed, these two guys, but I hope we will get done with them as well. And once we get done with this STA, then the STX and STY should be really trivial to implement. Okay guys, this is it from my side, so thanks for watching. Hope to see you in the next live coding session on this project. Until that time, and take care.